Hello and welcome to a brief presentation and demonstration of our discrete optimization software. Now we call it discrete optimization for and in the cloud because our capabilities are driven by an API and we are in the process of deploying this service so that it can be accessed as a cloud service. In this presentation and demo, I'll focus on the core features that we support and show the software running locally. So optimization is really about answering what is the best, fastest, shortest, longest, kind of objective in some context. So an example use case may be we have a bunch of we have some supply, and a set of demands. And we might ask, can we meet those demands given our supply? And perhaps also, if we can, what is the best way for the supply to meet those demands? Now, such a question would be quite easy when the supply and demands are, for example, whole numbers. So, for example, if my supply is 50 and I have 4 demands, one of which is 3, another 12, another 8, and another 21, it's very easy to check whether the sum of those demands fits, meaning does not exceed our supply. However, such a question is much harder when we're trying to fit items in bins. So I have these 8 distinct items to my left, and I have 5 bins, and my challenge is to be able to fit those items in the bins without overflowing any of the bins. Now I have seemingly made this problem easier by making the width of the bins and the items the same. So the only issue is the sort of the length or the height of the items and making them fit. Now it turns out that for that particular example, I can indeed fit those items in 5 bins, and I show here one way of doing that. But that would actually not be the best way of doing it, in the sense that it does not minimize the number of bins we need. It turns out that we can, with a little bit of ingenuity, we can fit those items in only 4 bins. And it turns out that any fewer number of bins does not suffice. So what does all of this have to do with cloud applications? Well, we can perceive a cloud application as comprising several components, for example, several units of compute, each of which has certain attributes, for example, how much memory it needs, how many vCPUs it needs. We might have different kinds of storage. So really a cloud application is a distributed application with several components, and these components may need to communicate with one another. And suppose we're given certain resources, for example, servers, maybe perhaps themselves in the cloud, some ways in which they can communicate. The question is, well, what is an appropriate placement of those applications on those resources? And indeed, do those resources suffice? And if the answer is yes, what is the best way that we can place the application on the resources so that we're making the best use of the resources? Now, our way is to encode this as a graph. And of course, the graph-based approach is fundamental to the software. Here is what we can call the graph optimization problem. We are given a set of demand graphs, and I show 3 examples to the far left of what I call demand graphs. We're given a supply graph, and our challenge is to ask whether we can place the demand graphs and the supply graph without exceeding any of the values in the vectors that we show. So as an example, the demand node with UID 0 to the far left top corner there, it's got a triple 1, 2, 3. We can think of this as, for example, a unit of compute, which requires 1 gigabyte of memory, 2 vCPUs, and 3 vGPUs. Now the edge between the demand node labeled UID 0 and UID 1 has an attribute value. It says UID of 12, but it has an attribute value of 5. So we can think of this as, for example, the minimum network capacity, like bandwidth, that is needed in the communication between the demand node 0 and the demand node with UID 1. And the question is, all these demands, can we simultaneously place them on the supply? And further still, if the answer to the first question is yes, we can indeed place them, what is the best way to place them? So what is a way of more precisely characterizing best in this context? Well, we could say we want to place the demands in a way that the number of supply nodes that we use up is minimized. Or alternatively, we could say we want to place the demands on the supply in a manner that the number of supply edges that we use up is minimized. And these would be two different optimization objectives. Now, we presented two examples of problems, graph optimization, and earlier to that I presented bin packing. Now it turns out that graph optimization, the problem is highly expressive. It can in fact capture or encode bin packing very easily, and also many other kinds of components that arise in cloud computing. So for example, anti-affinity constraints. An anti-affinity constraint is I'm given, for example, two computes or two VMs, for example, that I want to run in the cloud, but I do not want both the VMs to be placed on the same rack, server rack, because I really have two VMs for the purpose of redundancy, and if one of the racks goes down, I don't want my entire cloud application to be down. So that's an example of a constraint we can easily encode in our graph-based approach. Now, this graph optimization problem and even the seemingly easier bin packing problem are both NP-hard, which means that we do not anticipate that there's an efficient algorithm for them. So then, of course, the natural question is, well, what is our secret sauce in our software? So here, somewhat abstractly, I kind of say what it is. What we do is we map or reduce instances of the graph optimization problem to a canonical problem called Boolean circuit satisfiability, and that a problem encoded as a Boolean circuit satisfiability problem, we are then able to feed to a constraint solver, which then cranks and then gives us the answer. Now, moving on to the demo, and I just want to point out that in our demo we use as an example exactly this example that I show in this slide. So moving on to the demo, right, so we launch our software. We have, if you've seen our demo on the graph database, you've seen the suite of services that we have to the far right corner. I launch the CLI service and I upload a YAML file which encodes or specifies exactly the demand and the supply graphs that we had in the slide. So that's our first step. And once we do that, we can go back to our software, we can go back to the graph database microservice and take a look at the graph if we like. So all we have to do is go to the far right corner and choose the graph database, and there is exactly our demand and supply graphs that were in the slide. Now we can click on some of these and look at the attributes. This is something we've already seen in the graph database demo. So for example, that demand node, has a set of attributes. So for example, it says the number of vCPUs it wants, the number of GPUs it wants, the memory. And now we want to do the optimization. So at the front end, we have three options. One is no optimization, which is we're just asking, can we place the demands? Can the supply meet the demand? Now here it turns out the answer is yes, and here it shows we have chosen for the front end to pop up and show us a solution if one exists, and it actually shows the manner in which the demand nodes are placed on the supply nodes. Now our software is really API driven, so the front end is primarily for demonstration purposes. It is usable, but it's really we seek for the users to use primarily API driven approach. Now, once we get the placement, for example, we can go examine and it'll actually tell us as an attribute. For example, in this case, the demand node 5 is placed in supply node 7. And to the far left, we have other optimization objectives we can choose. For example, we can choose to minimize the number of supply nodes in a solution. So this should actually give us, if we run the optimizer, we should get a better solution from the standpoint of supply nodes. And indeed, earlier we had 5 supply nodes that we needed, but now we need 4 only. So it turns out that the minimum number of supply nodes we need is 4. And we can also choose another objective, which is to minimize the number of supply edges. And it turns out that if we choose that, then and we're willing to use up 5 supply nodes, then we can make do with 2 supply edges only.